Hello everybody and welcome to your video notes on Learning Target 8.5, which is all about circuit calculations. So if you want to set up your notes like this is the first thing that we're going to be talking about. So the main question is, how do we analyze circuits, especially the different kinds of circuits that there are? So one question you can write down is, what are the two arrangements of resistors? Because there are going to be two different ones. And then the rest of your notes can come over here. So in previous notes, we've talked about how we got like this. This is one way you could visualize the way a circuit works. It's not actually how it works, but it might help you understand. You've got your battery pump there in blue. I'm not going to move my mouse, otherwise that little line pops up. But you got your battery pump, which is kind of like lifting the electrons up higher. I'm going to move my mouse. And then they come around, and then they get to the first resistor, which is like a pump or a wheel that uses up some of the energy in the electrons, and then that drops it lower. So kind of like it's losing some energy. And then it comes here, loses all of its energy, goes down to the ground, comes back to the battery, and it lifts them up, gives them more potential, and goes on. So this one we got two in a row. All the current goes through all of the resistors. You can see that. All of the resistors have the same current, but could have different voltages or different potentials, right? Like you could have more of a drop here than over here. But all of the electrons are going through each of the pumps. They're all in a row. Over here, you can see that we got the same pump going through, and then some of the current, like some of the electrons, are going through the 30 ohm resistor, and some of them are going through the 10 ohm resistor, but not all of them are going through them. Just like over here, they're all going through, all of the electrons, all of the little plus signs are going through all of the wheels. Over here, they're kind of split, okay? But notice that the drop is the same. They have to go all the way back down to the bottom. So the current splits between resistors. All the resistors have the same voltage or the same potential drop. You see that? They all go to the same height, but they could have different currents, right? Like over here, you see that this 10 ohm resistor has more current going through it. It's going through it faster, whereas the 30 ohm resistor does not. So this one on the left is known as a series circuit, and the one on the right is known as a parallel circuit. This little message, this little all resistors have the same V, all resistors have the same I, you're going to want to circle that. If you have a highlighter, highlight that, put stars around it, something, because those are going to be big ideas that you're going to want to come back to. Okay, moving on. So, just ask yourself right now, what do you think these are? Because over here, these weren't actual circuit diagrams, whereas these are. Here you've got your battery, you've got your resistors, you've got your battery, you got your resistors. So the question is, which one is series and which one is parallel? Well, hopefully by the end of this slideshow, you'll be able to come back to this and go, oh, I know which one's which now. All right, so here we have three resistors in a row, and you may have predicted it, but this is an example of resistors in series. They're coming one right after another. So then my question that I have here is, does adding more resistors in series make it easier or harder for the current to pass all the way through? Well, sometimes it's hard to, well, not sometimes, but very often it's hard to visualize what's actually happening in a wire with electricity. So just like how we have like water analogies or like those pump analogies, we're going to use a toll booth analogy. So you've got a bunch of cars on the highway, and they all have to go through a toll booth in order to continue on to the rest of the highway. You got to pay the person their money. It's probably like $1 or something, and then traffic resumes. So this would be an example of a single resistor where all the traffic gets slowed down to one toll booth. That's like if we had one resistor in a circuit, that's why you have a slow current, because it's kind of like everything's getting pinched off like this. Well, 3 resistors placed in series ends up looking like this. where this person has to stop, and then they have to stop there, and then they have to stop there. So since they're all in a row, you can imagine that the traffic gets even slower. You can see in this little analogy picture, you only have one car here, whereas there's 4 there. So the current ends up being much slower if you have them all in a row like this. So the total resistance, of multiple resistors in series, you just add them all together, which kind of makes sense, right? So if the first one was, if they're all 1 ohm, you'd have 1 plus 1 plus 1, and you'd have 3 total ohms of resistance. It's like having one big resistor. So let's say we have an actual circuit here. Instead of having little symbols, I put in the pictures because hopefully that's a little bit easier for you to visualize. So what would the total resistance be? See if you can figure that one out on your own. And then using Ohm's law, what would the total current be? So go ahead and pause it if you want to try doing it on your own. But I'm just going to go over the answer now. So if we want to know what the total resistance is, well, we just have to add these all together because they're all in a row like this. So I do 2 plus 1 plus 3, and you end up getting 6 ohms. Hey, that's not so bad, is it? And then if we want to know the total current, you have to do 9 volts divided by 6 ohms, V divided by R, and we get a total current of 1.5 amps. Once again, not so bad, right? Series circuits aren't so bad. The one that gets a little bit more confusing are parallel circuits, but again, if you break it down and understand why this is happening, then hopefully it makes a little bit more sense. So we've got resistors in parallel now. And again, if I'm going too fast, you just go ahead and pause this video and you can rewind, or if I'm going too slow, you can always fast forward through it too. So then the question is, does adding more resistors in parallel make it easier or harder for the current to pass all the way through? Well, in the previous one, you'd think it's common sense. If you add more resistors, there's going to be more resistance, so then it's going to be harder for the current to pass all the way through, right? Well, turns out in parallel, that's not the case. It ends up making it easier for things to pass through. And here to help you visualize that is the toll booth again. So you got the first one with 1 toll booth, and then here you got one with 3 toll booths that are side by side. They're in parallel with each other, just like these resistors over here. 3 resistors placed in parallel enables the traffic to flow better, because it's kind of like you've got multiple alleys open. So this guy can go here, this guy can go here, this guy can go there, and then the traffic keeps moving at a faster pace. AKA the current is higher for this because more stuff is going to be able to flow through. And each one only has to go through 1 toll booth or 1 resistor. Kind of makes sense, hopefully. So, in order to make that work mathematically, you end up with this equation, which looks a little intimidating, but it's not so bad actually. I'll show you an example and I'll show you how to work through this, and like I said, it's not so bad. So the total resistance in parallel, if I move my mouse, the little thing pops up. But the total resistance is 1 over the total resistance equals 1 over the first resistor plus 1 over the second plus 1 over the third, and so on and so on and so on. Okay? So that one might be harder to do in your head. So I'll show you exactly how to do that. So here we go. I'm going to move this over to a platform that I can actually write on. Okay, so here we go. So what is the total resistance? Well, remember 1 over RP for the parallel equals 1 over R1 plus 1 over R2 plus 1 over R3. And resistor 1, okay, so then I'm just going to substitute in the resistors. I'm just going to call this guy R1, this is an R2, and this is an R3. Does not actually matter which one's which. It all ends up working out in the end. So if you called the first one 2, the second one 3, the third one 2, whatever, it does not matter. But that's just how I'm going to do it. So 1 over Rp equals 1 over, so R1 I said was 2 ohms, plus 1 over 1 ohm, plus 1 over 3 ohms. So let's just zoom in on this because that's the interesting stuff for now. And so what I'm going to do is I'm just going to change these all into, so we could look at like fraction rules, and we could look at like, oh, what's the least common multiple on the bottom, and get the same denominators, add them up. That just sounds complicated, but totally possible. The easiest way to do this is just to change each of these to decimals and then go from there. So 1 over 2, that's the same as 0.5, and I'm just going to drop the ohms. Plus 1 over 1, well, that's just 1. Plus 1 over 3, you can always grab our calculator and double check, but that's just 0.333, and so on. If you get a repeating decimal, let's just toss it in 4 for good measure. And that all equals 1 over Rp. So I'm just going to add these all together, and I end up with 1.8333 equals 1 over Rp. Okay? Now, there are a couple ways we can go about getting this. The best way is just to think about your algebra. So algebra tells us if I want to get Rp, because we want to find out what Rp is, not 1 over Rp. So in order to do that, I have to multiply by what's on the denominator. The one on the left goes away. So I'm left with 1 equals 1.8333 times Rp. And then I divide by 1.8333 divided by 1.8333. It goes away. I'm left with Rp equals 1 divided by 1.8333. And I'm left with 0.545 ohms. And there's more decimals to that, but that's just what I got if I round it. Okay? So that's what we end up getting. Okay? So the math, it seems a little complicated, and this part, let's see. This part right here might seem confusing to you, but if you look at it and just think, oh, I got to get Rp by itself, then you just think, oh, I always have to multiply by what's on the denominator to both sides. So then I'm just left with the 1 over 1.8333, and then we get our final answer there. Okay? So that was our total resistance, and then the total current. We just use Ohm's law again, so I equals V over R. So my voltage is 9 volts from the battery divided by the 0.545. Yeah, ohms. I end up with pretty much 16.5 amps, because I got 16.49, so that's pretty much 16.5 amps. So there we go. And I have all the answers here, and that's exactly what we got. So this was the one in series. This is the one in parallel. And notice that we had the same resistors with the same light bulbs, the same battery. And our resistances and our currents were completely different. I had more resistance for the one in series, right? I had way less resistance for the parallel one, but then I had a lot more current for the parallel one, and a way less current for the series one. It's kind of like the traffic, right? If there's more stuff in the way, there's more toll booths in the way, everybody has to go through this, then the current is going to be slower. That's the 1.5 amps. Whereas over here, everybody can go through their own. Everybody really only has to go through one light bulb, right? The traffic splits, they choose their own path. So then the current can go much faster. Like the traffic gets much faster with this because everybody has a choice. So that's all I got for this video. In the next one, we're going to be talking about how to do, like how to calculate how much voltage is used by this light bulb, how much voltage is used by this light bulb, and so on. So that's all I got for this one. Thanks for listening.